All right, we're going to go through this example problem of what is the pH of in a case where the quadratic equation is necessary, and we're going to do it without the quadratic equation. It only requires simple algebra, but you do have to keep track of stuff. So let's walk through it and see how this goes. So what is the pH of 0.31 molarity cyanic acid? And so we go through our flow chart and say, is this an acid, base, or a salt? And of course it's an acid. Big ol' hint right there. And so as an acid, then the next question we ask ourselves is it strong or is it weak? And it is a weak acid. We know that in a couple of ways. It's not on our strong acid list, which we should have handy. Additionally, if we look at the Ka table, we do see cyanic acid is listed as a weak acid on that Ka table. We can get the formula from there, but you don't have to. You can always treat it with the generic formula from here on out, unless the question is specifically asking about the chemical formula. And we've seen a couple questions like that. So there's the formula for cyanic acid. So once we decide it's a weak acid, we know the next couple steps involve, we've got an equilibrium constant. We need to draw an ice table. We look at the Ka value. From that ice table, we can get an X, which is the hydrogen ion concentration, which gives us the pH. Sort of those steps fall in line once we've identified that it's a weak acid. And so here is our generic equation for our ice table, 0.3100. And we look up our Ka value, and it is 2 times 10 to the minus 4. This one only has 1 sig fig in our table. Most of them have 2 sig figs. This one only has 1. We're still going to go to 2 decimal places on our pH. Remember that the formula for Ka looks like this, and we need the equilibrium values to put in that Ka table. And so that's where we're going from. So as we start putting in values, 2 times 10 to the minus 4 equals x squared all over 0.31 minus x. We'll use the approximation. Down here, we'll say that 0.31 minus x will approximate it to be 0.31. As long as x is small enough and 0.31 is big enough, this works. And I have suggested in previous videos that you should always start with the approximation. So but just because the math is so simple, and then you can always figure out if it works later. And just a tip on a multiple choice question, if you use the approximation method and it's not quite good enough, most of the time you can still pick it out of the lineup. I'm not asking you to do anything nefarious here, because we also see questions where you actually have to type it in. And if it's not close enough and you type it in, you might get counted wrong. So this is one of those situations where we have to kind of figure out what's going to save us the most time. And so using the approximation almost always saves you time, regardless of whether it works or not. So if I make that approximation, this becomes my formula. I solve for x. Let me plug it in. And I get x is equal to 7.87 ... times 10 to the minus 3. I'm going to store that. Now, as we look at it, and you need to kind of get a feel for this, that's saying that if I take it out of scientific notation, it's 0.00787 ... So basically, it's a digit in the third decimal place. And I went on the assumption that 0.31 minus this value, or something very close, was approximately equal to 0.31. And that's not quite right. Since this is in the third decimal place, it starts affecting that third decimal place, which affects the rounding at the 0.31. So this is not a great approximation. I can go with this approximation at this point if I did find that the approximation was fine. If this went out a couple more decimal places, for example, I'd be ready to calculate the pH and move on. Or if this is a multiple choice test, I'd go ahead and calculate the pH, and I'd see if any of my answers down there were very, very close to it, and then make sure there weren't a couple that were very, very close to it. But this approximation doesn't work so great. So we're going to do the method known as successive approximations. I think I spelled that right. This is the method of successive approximations. It looks like an awful lot of double letters, but I think that's right. Essentially what the method of successive approximations says is come back, oops, not to that one, come back to this original equation. 2 times 10 to the minus 4 equals x squared all over 0.31 minus x. We were approximating that we could get rid of that minus x, but to do the successive approximations, what we say is, well, instead of getting rid of it, let's go ahead and plug in our first value of x for it and solve for x, the x in the numerator again. So I would essentially set up 2 times 10 to the minus 4 equals x squared all over 0.31 minus 7.87 times 10 to the minus 3. And I would solve for the x in the numerator. Now I don't have to write it out. I'm sitting here on the calculator with that 7.87 times 10 to the minus 3 stored in my memory. If you were smart, you did that too. And so I'm going to make it negative. I'm going to add it to 0.31 and hit my equal sign. So I'm going to do this bottom part. Let me do it. I'm going to do this bottom part. So I'm going to do that calculation, hit my equal sign, and then I'm going to multiply by 2 times 10 to the minus 4. And then I'm going to take the square root of it to get my second approximation, and we can call this x2, and it is 7.77 ... times 10 to the minus 3. Now look how close it was to 7.87, 7.77. So it's off in the second significant figure. 7.8 versus 7.7. That second significant figure is different. We want to keep doing this approximation until it's the same through about the third sig fig. That means we've honed it down. This is a mathematical way to kind of narrow it down and focus in on exactly what the value of x would be in this original quadratic equation. I mean, that's ultimately what we want. What is the value of x in that original calculation? It's just once you get used to punching it in your calculator, it's just much quicker. And so we're going to do, now that we've got the second approximation, we're not stopping yet because it's not close enough to the previous approximation. We'll do a third approximation, or first a second approximation. No, that was the second. We'll do the next approximation. And the next approximation says to take this value, this new value of x, and plug it back into this equation. And again, you don't have to write this out, but I am so that you can see exactly what I'm doing. And again, I'm sitting here with this value in my calculator. Don't round it. And I'm going to make it negative and add it to 0.31. I'm going to make it negative and add it to 0.31 and hit my equal sign. And then I'm going to multiply by 2 times 10 to the minus 4 and hit my equal sign. And then I'm going to take the square root of it. And what I get for my third approximation, my next approximation, is 7.77 ... times 10 to the minus 3. That's good enough. We're now at the point where we have 3 digits that are staying the same. And it is this value of x, remember x is equal to h plus concentration, that I'll go ahead and use to calculate my pH. And I get 2.1093 or 2.11. Is that exactly the same? Nah, that's not quite the same thing. We got 2.10 approximating. If you solve the quadratic equation, it would also get you a pH of 2.11. If you solved the quadratic equation exactly, it should give you this to the 3 digits, and it should give you a pH of 2.11. Depending on what the value of x ends up being after the first approximation, you may need to do this 3 or 4 times. We got to stop on our 3rd time. So doing it 3 or 4 times is not unusual, but again, you don't have to write it out once you get used to plugging it in your calculator, and it can go very, very quickly.